Hello everybody, so this is the second problem solving session for chapter 1. We have only one problem. In this problem we are going to analyze a RLC circuit by using phasors. So what you see here is a time domain RLC circuit. We have a 10 ohm and 10 ohm R1 and R2, and then a capacitor 0.05 farads, and then an inductor 0.5 Henry. The generator potential is given as 5 cosine 20 plus 45 degrees volts. So to analyze this, first we need to draw this same circuit with the complex impedances. So we need to turn everything into phasors. When we turn everything into phasors, when you turn the source, it's called phasors, but when you turn the capacitance and inductance, it's called the complex impedances, right? So here's how we turn the elements into complex impedances. The resistances turn as themselves, so they don't change. And then the capacitance turns as negative J divided by J omega, C omega, negative J divided by C omega. And then the inductance turns as J omega N. So here's, if we just plug into these formulations, we can derive these. They are all coming from, let me just show you how the capacitance is just derived. So here's the expression for capacitance, current, ICT is equal to C dVCT dt, right? So if you turn both sides into phasor, here is the phasor for current, and then we have C. Now if we take the derivative then of exponential, we have J omega, right? And then Vc, the phasor for the potential, right? So complex impedance really is just like resistance. So we need to divide the potential. How do we calculate the resistance? By current. And then I'm gonna put C, J, omega on the other side. Now, we don't really like this J in the denominator, so we like to carry it in the numerator. How do we do that? We multiply by negative J. That's how you get the complex impedance for the capacitance. And the inductance, the complex impedance for inductance actually works the same way. So let's continue by plugging in our numbers in these formulations. If we calculate the complex capacitance, that's negative 10J, complex inductance is 10J. So if I just draw our phasor domain circuit, we have the phasor for the source, and then we have our first resistance. Remember, the resistances just go to phasor domain as themselves. And then our second resistance, and then usually the symbol for complex impedances are these little boxes, and you can just call it ZC for the capacitance, and then ZL for the complex inductance. So if you want to analyze the circuit, let's say you want to calculate the current going on. Of course, since you are doing it in phasor domain, what you're calculating is really the phasor for current. Everything works exactly just like the resistive circuits. So how would you do it? You would combine all of these guys because they're parallel, and then you would just add it to R1, and then you would just divide that number by this Vs. So that's exactly what we are doing here. We're combining R2, ZL, and ZC, and then coming up with an equivalent impedance. And if you calculate those, you get 1 over 10. This is just working by complex numbers. And then if you just add that complex impedance to R1, because they are series, then you get 20 ohms, right? And then it's time to write the phasor for the potential. Remember the time domain expression for potential. And now we need to take, for phasor, we need to take the magnitude, and then we need to take the phase, right? That's exactly what you see here. It's 5 e to the j 45 degrees. So all we do is divide this potential by our complex resistance or complex impedance, and then we get our current. So the phasor for current is this, And then if you want to switch to time domain, all you need to add is the frequency. So if you look at this current, you see that there's no phase change because of the circuit. You can call this as a no phase change circuit because of the balance. And we have some magnitude change in this specific circuit.